Conformation of alkanes. Conformation of alkanes deals with the isomer of alkanes that form due to slight changes in their structure, especially in their carbon-carbon bands. The conformations start with ethene and occur in all alkanes higher than ethene. At a molecular level, a property of sigma bonds in alkane is that the bonds keep on rotating. For example of ethene, one methyl group is able to rotate about the carbon-carbon bond freely without any obstacle. Conformation, any one of infinite number of possible spatial arrangement of atoms in a molecule that result from rotation of its constituent groups of atoms about single bonds. In the organic chemistry, it is found that you can rotate a single bond of a molecule to change the arrangement of atoms without changing the chemical formula of the compound. So, isomers of compound can be created by different forms of rotation about one single bond. So, the different arrangement of atoms due to such rotations of bonds are known as conformations. As we know, alkanes have simple carbon-carbon single bond in higher alkanes. There is no such bond in methane, but ethane onwards all alkanes have a carbon-carbon single bond. So this allows rotation of these single bonds to form a different spatial arrangement of carbon atoms, forming different conformation of such alkanes. When you see an ethene structure, you will notice the single CC bond, and every atom is also bonded to 3 atoms of hydrogen each. Now, in the first conformation, the hydrogen bonded to the first carbon atom will line up with the hydrogen of the second carbon atom. The angle between the two planes is the dihedral angle is 0. So if you see the first hydrogen atom can be said to be eclipsing the second one, therefore this is known as eclipse conformation. In ethane conformation, the eclipse conformation is unstable. The two hydrogen atoms that line up together have favorable interaction. They repel each other. So staggered conformation of ethane requires less energy to be maintained and is more commonly found. Newman projections. This is one of the ways to represent conformation of alkanes. It visually represents the bonding of atoms from front to back. A dot represents the first carbon atom, the one that is nearer. The further carbon atom is a circle lines show the hydrogen atoms bonded to each carbon atoms. This representation clearly indicates the dihedral angles. Sohor's projections. These represent the conformation of alkanes in form of straight line. The first carbon is at the lower end of the line on the left side, and the second carbon is the upper end of the diagram. Here, the lines attached to carbon atoms show hydrogen atoms. The different spatial arrangement of atoms groups that result from the single bond rotation are called conformations. Molecules with different conformations are called conformational isomers or conformers. The two extreme conformations of ethene coming from the CC rotation shown above are the staggered conformation, with all of the H atoms spread out, and the eclipse conformation with all the H atom overlap. Conformational energy, the relationship between molecular structure and potential energy, is a major area of study in organic chemistry. In conformational analysis, because we are interested in relating the structure of conformers to their energy, and therefore to their relative stabilities. In an eclipse conformation, the carbon are aligned so that the hydrogen are lined up with each other. This creates steric hindrance between them. In a staggered conformation, the atoms are all equally spaced from each other. Conformation are the different arrangement that result from sigma band rotation in organic chemistry. A conformational isomer, also known as a conformer, is a specific conformation. We must first study the concept of conformational isomerism, which deals with rotation around single bonds before moving on the stereochemistry and chirality. Sigma bonds in alkanes have the property of revolving the molecular level. In ethene, 1-methyl group can freely spin around the CC band without hitting any obstacles. It is extremely recommended that you use a molecular model to see the band rotation. With a molecular model, you can rotate one methyl group while holding the other one steady. Rotation around the band is the straightforward since the sp3 orbitals overlap and the link is cylindrically symmetrical. Therefore, the molecule seems to remain intact. In the study of conformation, it is convenient to use certain types of structural formulas. Conformation analysis of propane. A similar analysis can be applied to propane as well. There are still two types of conformation, staggered and eclipse, resulting from the rotation. The difference between propane and ethene is that there is a methyl group connected on the rare carbon for propane. However, that does not affect the relative stability, and the staggered conformer is more stable and lower energy. Conformation analysis of butane. There are 3 CC bonds in butane, and rotation can occur about each of them. If we choose C1, C2, or C3, C4 for the study, the situation is almost the same as propane, with the ethyl CH2CH3 group replacing the CH3 group. However, if we consider the rotation about C2-C3 band, the situation will be much more complex. An understanding of the forces at work and the energy associated with these processes is important because the structure of a molecule can have a significant influence on the molecular properties, including dictating the outcome of a reaction. Although the ideas are developed for the simplest functional groups, the alkanes, these same principles can be expanded and applied to other functional groups.